Hello and welcome back to our discussion on support vector machines. So, we were looking at the optimization problem corresponding to the optimal separating hyperplane, right. So, to solve this problem, right. So, one of the techniques for solving these kinds of constrained optimization problems, okay, is to set up a Lagrangian which essentially looks at the original objective function, which is half beta squared, and a second component corresponding to the constraints that we have. Okay. So, if you look at this quantity in the square brackets here, so you can see that this is the term on the left hand side of the inequality and that is the term on the right hand side of the inequality, right. And we really want to make sure that this difference, right, is not negative, right. If this difference is negative, then that would mean that yi times xi transpose beta plus beta naught is actually less than 1, right. We do not want this to be negative. So, what we essentially say this is we then add it here as with a minus sign, right. So, this essentially means that when I minimize this whole expression, right, so this term will become as large as possible, as largely positive as possible. So, that essentially means that I am going to try and make this as larger than 1 as possible, right. So, this term here alpha I lets me control how much weight I want to give to satisfying the constraints versus how much I really want to minimize the objective function, right. So, we really need to satisfy the constraints as much as possible, and since there are solutions that will be that will satisfy the constraint and give you a good optima, right. So, we should essentially be trying to drive this thing to as large a value as possible, right. So, this is called the primal of the problem, and your goal is to minimize the primal, right. So, I am going to do something fairly technical right now. So, if you do not understand all of it in the first go, that is fine. You might have to do a little bit more reading on the side, but this is essentially to give you an idea of how people go about solving these kinds of problems, right. So, we are going to try and create what is called the dual of this, the primal objective function, right. So, the dual is a way to create something, create an optimization problem that is simpler to solve in some sense than the primal, okay. And the dual at all points provides you some kind of a lower bound on the kind of solutions that you can achieve with the primal, right. And at the optima of the dual, you would ideally like the optima of the primal also to be achieved. So, you are going to create a problem called the dual, you are going to solve the dual, right, and when you reach the optima of the dual, you would like the optima of the primal to be also achieved. The same solution that gives you the optima in the dual problem should give you the optima in the primal problem, right. And there are technical conditions under which this is satisfied, right, and we are not going to go into those technical conditions. I am just going to give you a flavor of the kind of results that we will be looking at, right. So, let us start by setting the derivative of LP to 0, okay, derivative with respect to beta and beta naught, okay. So, taking the derivative with respect to beta and setting it to 0 and solving for beta gives me you can figure that out by little bit of algebra here, right. Likewise, setting that derivative with respect to beta naught to 0 and solving it gives me right. So, I can substitute these back into the primal problem, right, and do a lot of algebra, right, do a lot of algebra really, and then I can simplify this and I will get what is known as the dual, right. Let me write the dual here. Okay. So, this is just really obtained by substituting your beta into the expressions here, right, and then using the fact that alpha I y I would be 0 at the optima. So, that is the thing, but then it is subject to the constraint So, note that I said so your dual is always going to give you a lower bound on the solution of the primal problem. So, really if you are minimizing the solution in your primal, you should be maximizing the solution in the dual, so that the two of them can coincide at some point. So, essentially you would be maximizing this, right, subject to the constraint that all your alpha i's are greater than or equal to 0, right. So, if we think about it, this is a much easier constraint to wrap our heads around, because it just says that hey, you will only be doing it in the positive coordinates, right. And while this had a more complex set of constraints, so we have kind of reduced the constraint into something easier, and therefore the dual problem is sometimes easier to solve. So, for the dual and the primal to be at the optima at the same time, right. So, we really want them to satisfy a set of conditions which are essentially to with the derivative of the primal problem. So, we require that this should hold, we require that this should hold. I am going to write them as 1, 2 and 3. In addition, we require that this condition should also be require that this condition should also be satisfied. These are called the KKT or the Karush-Kuhn-Tucker conditions, right. And so, for the optimization problem to have the same solution, we require that the KKT condition should be satisfied, right. So, once you have an optimal solution for the dual and the primal problem, because these KKT conditions have to be satisfied, you can make certain observations, right, especially when working from condition 3 here, right. So, if alpha I is greater than 0, right, if alpha I is greater than 0, so what does it mean? So, this has to be equal to 0, then the term in the square bracket has to be equal to 0. Right, that means yi into xi transpose beta plus beta naught should be 1. So, what does that mean? It means that it is exactly on the edge of the margin, right, when it is equal to 1, because greater than or equal to 1 is what we needed to satisfy. So, when it is equal to 1, that means it is exactly on the margin, right. Likewise, if so if the quantity in the square bracket is greater than 1, then alpha I has to be 0. So, that essentially means is if your data point is something that is far away from the hyperplane, that is more than the margin away from the hyperplane, then the corresponding alpha i's will become 0. Okay. So, what does this mean for us? So, if we think about it, so the solution that we get, right, which is essentially beta, that is the solution that we want to get, right, is formed by taking the product of alpha i's, y i's and x i's, right. So, if I am saying an alpha I is going to be 0, it essentially means that the corresponding x I has no role to play in determining what my beta should be, right. If I say that, it implies if x I is 0, that implies that x I has no role in computing beta, right. So, which are the data points which will actually affect the solution beta? They are exactly those points for which y I times x I transpose beta plus beta naught is 1. That means, they are exactly the points which lie on the margin, right. So, only these points will influence how the solution beta looks like, right, and all the other data points that you have which are farther away from the separating hyperplane than these points do not matter in the solution. Okay. So, these points are called support vectors. So, do note that you really do not have to solve these optimization problems yourself. There are enough tools that actually can do it for you. The whole goal of this lecture is to get you to appreciate what is it that you are doing when you are using a support vector machine for solving a problem, right. So, at the end of the day, all you are going to do is fire up a tool that is going to tell you what is the separating hyperplane given a bunch of data, right, but it is good to have an appreciation of how the classifier is actually built, right. So, once you figure out a beta, right, then I can substitute that into the KKT, the third condition here, and solve for beta naught. Okay. So, typically what you do is that you use every xi that is a support vector, right, and you substitute that here and then try to solve for beta naught, and typically you end up taking the average value of that. Okay. So, a couple of things which I want to point out about support vector machines. So, one thing is you should be very clear that the training data, okay, none of the training data will fall within the margin, okay, but that is not to say that the test data might not fall within the margin, right. the test data might fall within the margin, it might actually fall on the other side of the hyperplane. So, for all we know that the test data, I mean there could be errors on the test data, it is just that on the training data, okay, it tries to fit something that is as far away as possible from the data points. Okay. So, the idea here is that, so if I give as much gap between the classes as possible, right, then the classifier would be more robust to noise on either side. So, this is assuming that your noise could be in this class or in this class. If you know for sure that one class is noisier than the other, or if one class is more valuable than the other, so you might want to actually modify your objective so that the line does not go right in the middle, but it moves to one side or the other. So, having said that, under the assumptions of the support vector machines, if the assumptions hold good, then it is a very, very robust classifier. So, the reason is it pays attention only to the points that are closest to the class boundary, you know. So, I can have as many data points here as I want, I can have as many data points here as I want, right, of the corresponding class. It really does not affect my classification, because truly the ones that are close to the boundary are the ones that need attention, right. So, that essentially makes support vector machines more robust, right. Right. On the other hand, if you are going to have some kind of a stochastic process that is generating the data, right. So, if there are a few data points that are by chance or noise data points that actually are close to the hyperplane, right, that will affect the support vector machines tremendously, and therefore, it will try to reduce the margin by a large extent, while a classifier that looks at the entire data and tries to find a distribution for the entire data might be a little bit more robust to such kind of noise. Yeah, so, this is how you solve the basic optimization problem for support vector machines.